a cylindrical container of radius r equal to 1 meter. So this is the cylindrical container. This is diameter is 2r and radius is r, which is 1 meter. Wall thickness T is 1 mm. So r is 1 meter, whereas T is 1 mm. So this is obviously a thin walled cylinder, because d by d by t, di by t is what? 2000. Obviously it is a thin walled pressure vessel. Thickness is 1 mm, filled with water up to a depth 2 meter. So here it is mentioned 2 meter, this is 2 meter. So water filled up to 2 meter and suspended along its upper rim. So this is the upper rim, it is suspended along upper rim. The density of water is given also. Rho is 1000 kg per meter cube, that is 10 to the power 3 kg per meter cube. It is given. Acceleration due to gravity, that is g, is also given 10 meter per second. The self weight of the cylinder is negligible. Weight of the cylinder is negligible, self weight. The formula for hoof stress in a thin wall cylinder can be used at all points along with the height of the cylindrical container. That is, along the height, that is this direction, circumferential expression of circumferential hoof stress is valid. Axial and circumferential stress, that is sigma A and sigma C, experienced by the cylinder wall at mid depth 1 meter. Where is mid depth? Say this is mid depth, which is 1 meter. This is also 1 meter, and obviously this will be also 1 meter because total depth is 2 meter. So we have to calculate what is the axial and circumferential stress, and here axial stress is denoted by sigma A and circumferential stress is denoted by sigma C, but our expression is axial is sigma 1 and hoop or circumferential stress is sigma 2. So here we have to calculate both the stresses at mid height. So here the depth is 1 meter. So what will be pressure at here? Pressure P is rho GH, rho GH. So this is the pressure here. Now what will be circumferential stress? Circumferential stress sigma C equal to sigma 2 is always PR by T. Always PR by T. Here it is denoted by capital R, so you can write capital R also. R is the radius of the cylinder. This is R. So what will be sigma C? Sigma C is sigma 2. Let us put the values. We know the value of P. We know the value of P. Rho G H. What is H? H is 1 meter. So into R by T. Now let us put the value. Rho is 10 to the power 3, a density of the water. G is 10. H is 1 meter. R is also 1 meter. And T is in millimeter. So we have to convert it into meter. That is 1 into 10 to the power minus 3 meter. So all are in SI unit. So this will be Pascal. The stress unit will be Pascal. So sigma C is sigma 2 is equal to 10 into 10 to the power 6 PA, that is 10 MPa. So we have determined the value of sigma 2, that is hoof stress or circumferential stress, is 10 MPa. Now we have to calculate axial stress. What is the axial or longitudinal stress? That is sigma A. Now sigma 2 for cylindrical pressure vessel is always PR by T. Sigma 2 is always PR by T. That we have calculated from our generalized equation. That was what I am recapitulating once again. Sigma 1 by r1 plus sigma 2 by r2 is p by t. This was our basic equation for thin wall pressure vessel. Now r1 for r1 is along this direction, radius of curvature is infinite. R1 for cylindrical pressure vessel is always infinite, so this term going to be 0. Now sigma 2 becomes PR by T. So always it is PR by T. This is a single equation and there are two unknowns, sigma 1 and sigma 2. So obviously it is a statically indeterminate equation or statically indeterminate problem. So sigma 1 or axial stress we always calculate from boundary condition. So what will be the boundary condition here to calculate the axial stress sigma 1 at this point, at this level? So at this level, if we take a section, that is say this it will be look like this. At this section, this is the vessel, and how sigma 1 is acting? Sigma 1 is acting on this area. Sigma 1 is acting on this area. Sigma 1 is acting on this area. So this is sigma 1 or sigma A, and what is the area? 2 pi r into t. So this is the force due to axial stress. Now we have to balance force along axial direction. Say this is the axial direction. So at equilibrium, all forces along axial direction must be 0. Now what is another force? Another force is what? That is nothing but the weight of the liquid. That is nothing but the weight of the liquid. So if say weight of the liquid is W, that will be balanced by that axial stress. So here this is balanced by what? Weight of the liquid. This is balanced by weight of the liquid. Sorry, I am once again weight of the liquid. So the equilibrium equation gives sigma 1 2 pi RT minus W is 0. Now from this equation we can calculate, or from this boundary condition we can calculate sigma 1. So sigma 1 becomes weight of the liquid divided by 2 pi RT, and sigma 1 is same at any section, at any height. If you take this height, this here also, that will be that stress will balance the weight at this height. Any height, sigma 1 is same, but sigma 2 varies on pressure. Here at the top level P is 0, so sigma 2 will be 0 there, but sigma 2 increased with the depth as pressure is increasing with the depth. But sigma 1 at this situation, when it is suspended, sigma 1 is constant throughout the depth, and this is the value of sigma 1. So what is sigma 1? Sigma 1 weight of the liquid is what? Pi r square into height of the liquid, that is capital H, say capital H, pi square rh rho into g, that becomes the weight, into 2 pi rt. So pi r square r cancelled, that is h rho g by 2t. Here h is what? H is the total height of the liquid, that is 2 meter. We are considering this h. If we have considered h here, then we have already considered h for half height here in sigma 2. So let us, there may be a confusion, we can denote the total height by h prime. Total height is h prime. Total height of the liquid column is h prime. So h prime is 2 meter here. So let us calculate. H prime is 2 meter, rho is 10 to the power 3. What is g is 10 2 into 1 into 10 to the power minus 3 as thickness is in millimeter. So this becomes also what? 10 into 10 to the power 6 Pa, that is sigma 1 is 10 MPa. So both sigma 1 and sigma 2 becomes 10 MPa at the mid height. So let us back to the problem. So both sigma 1 and sigma c are 10 MPa at the mid depth of the cylindrical vessel. So this option A is correct here. Now in addition, it is given Young modulus and Poisson ratio of the container material are 100 GPa and 0.3 respectively. The axial strain in the cylinder at the mid depth. So what is given? E is 100 GPa and mu is 0.3. And what we have to calculate? We have to calculate the axial strain in the cylinder wall at mid depth. What is axial strain? Epsilon 1, that is 1 by E. We will apply generalized Hooke's law, is sigma 1 minus mu sigma 2, that is 1 by 100 into 10 to the power 9. What is sigma 1? 10 MPa minus 0.3 into 10. Both sigma 1 and sigma 2 are MPa, so I am writing minus 10 to the power 6. All are in SI unit. Now sigma 1 becomes, this becomes 7. Here 10 to the power, total 10 to the power 11, and here 10 to the power 6. So 10 to the power minus 5. 6 minus 11 is minus 5. So this is the value of, this is the value epsilon 1, 7 into 10 to the power minus 5. This is the value of axial strain. Now let us back to the problem. Young modulus and Poisson is given, Poisson ratio is given. The axial strain in the cylinder wall at mid depth is 7 into 10 to the power minus 5. So option C is correct, and this is from GATE 2008. The figure shows a thin walled open top cylindrical vessel of radius r, radius is r, and wall thickness is t, it is mentioned. The vessel is held along the brim and contains a constant density liquid to height h from the base. So this is the height, and this is the liquid filled up to this. Up to this liquid is filled up. Neglect atmospheric pressure, the weight of the vessel and bending stress in the vessel walls. So weight of the vessel is neglected, atmospheric pressure is neglected, and bending of the wall is also neglected. Which of the plots depicts quantitatively correct dependence of the magnitude of axial wall stress sigma 1 and circumferential wall stress sigma 2. So what will be the variation of sigma 1 and sigma 2 with y? What is y? Y is this direction. So here it is 0 and this is the positive y towards downward direction. This is the positive y. So variation of sigma 1 and sigma 2 along y we have to determine. So this is a cylindrical pressure vessel. We know that this is a cylindrical pressure vessel. So sigma 2 is always PR by T. Now if this is the pressure vessel, that is, this is y direction. So this P increases with y. As y increases, P is increases, and R and T are constant. So expression of P is H rho G. Rho and G is constant because rho and G, that is density of the liquid, is constant. So P increases with H linearly. That is, as we go downward, that is along positive y, sigma 2 will increase as p is increasing linearly. So variation of sigma 2 will be how? That is variation of sigma 2, if this is y, this will be sigma 2. This will be the value of sigma 2. And the expression of sigma 2 is h rho g r by t. H rho g r by t. So this is the expression of sigma 2. Now what about sigma 1? What is sigma 1? If we take a section at anywhere, say here we are taking a section. How will it will look like? That is, I am drawing the isometric view at section AA. So here the sigma 1 is acting like this. So vertical force due to sigma 1, is what? That is sigma 1 into 2 pi RT, and that will balance. So this force, that sigma 1, will balance the weight of the liquid. So this is the weight of the liquid, and at any section, if we take this section, the sigma 1 2 pi RT is balancing the weight of the liquid column. So that is equal to weight. So sigma 1 is constant and it doesn't depends on the y. So along y, sigma 1 is constant at any level of the cylindrical vessel. And this is the expression of sigma 1. So sigma 1 is constant. So this is sigma 1. So these are the variation of sigma 1 and sigma 2. This problem I have explained earlier. So now let us come to the options. So sigma 1 is constant. So this is option A, sigma 1 is constant and sigma 2 is varying like this. So this is the correct one. So A is the correct one. And they are same at mid depth. They are same at mid depth. There was a problem in gate earlier, we have solved gate 2008. That problem was asked, what is the stresses at mid depth, and we have seen both was 10 MPa. The value was same. So from that you can take the reference of that problem to calculate the value. I am not here calculating the value, just explaining how they will vary. So this variation is correct one.